Okay, we're going to be talking today about, or not talking today, we're going to be doing a lab where we're testing pH. But it's kind of a waste of your time to do a lab where you're testing pH if you don't know what pH is. So I'm going to lecture first on what pH is, which starts with what are acids and what are bases. So we're going to learn today about acids and bases, and then we're going to do some tests to see what the level of acidity or basicness is in different household things. So we have here white vinegar, ammonia cleaner, table salt, baking soda, washing soda. I don't know what washing soda is as far as household cleaner. Something that is common in household that I didn't give you a name for, and borax, things that we're going to test. And for the testing, we're going to use this cabbage broth that I made. Yeah, she did. So let's first learn about acids and bases. First, acids and bases. The difference in acid and base, according to the, is it Bronze and Louis? I have their names in the next slide, I think it is that acids donate a proton and bases accept a proton. Now, what's in the nucleus of an atom? This is a very simple, redundant type of question. What's in the nucleus of an atom? Protons and neutrons. And if I have an atom with one proton, what do I call that atom? Look back there. Hydrogen. So if it's a proton donor, an acid donates a proton, that means an acid is something that's going to give up a hydrogen atom. So you have to understand the terminology here. Proton donor means it's going to give up a hydrogen atom. A proton acceptor for a base, it'll receive. And so these are just some pictures of first acids. Your citrus fruits are acids. Pickles are acidic. The toilet bowl disinfectant here apparently is acid. And your Coca-Cola. How many people have read that you can clean a toilet with Coca-Cola? Wow, I thought more would have read that. Well, it's certainly true because it's the acidic nature. And since the colas are pretty acidic, your sodas are pretty acidic, we're going to test a couple other things, and one of them will be club soda, also grapefruit juice. And if it's acidic, it should clean the toilet bowl. And so, is that a sign that it's bad to eat? Well, what else is acidic? Obviously, grapefruit juice is going to be acidic. Tomatoes are acidic. Does that mean we shouldn't eat them because they're acidic? No. Now, of course, Alex says yes. If it's very acidic, it's going to be dangerous. You do not want to drink hydrochloric acid. Tasty. No. Burns the esophagus. Yes. So those are some acids, and then here's some bases. So some bases, baking soda. Well, that's one of the things we're testing. Soap. End of last class period, we talked about soap. The soap is made so it has one end is polar, and then it has a long chain that's nonpolar. The polar end attaches to water. The nonpolar end will use dipole or induced dipole to attach to the grime. And then all of these soap things on the grime will then be lifted because of the attraction to the water from the other end and pull it away. And your drain cleanser, Drano. Those are basic things. So we use acids and bases a lot in life. And we, unless you're in chemistry class, you generally don't think of it. Now, some differences in acids and bases. An acid donates a hydrogen ion, right? It said donate a proton in the previous slide. Actually, it says donates protons at the top of this one as well. That's a hydrogen ion. Why ion? Well, it's the hydrogen without the electron. And acids taste sour. In fact, acidus, the Latin word from which acid comes from, means sour. This goes to one of Alex's themes of the year. Can you lick it? If you taste it and it tastes sour, it's probably acidic. So, you've got your little sour, what do they call it? Sour Patch? Sour Patch Kids? Yeah, okay. That's, are they acidic or basic? They must be acidic because they taste sour. You might start salivating. I'm very Pavlovian. Bases, on the other hand, are going to accept a proton, accept a hydrogen atom, and those bases feel very slippery. And they're bitter to the taste. So something that's bitter is basic. And we also call them alkaline meaning ash. So if you are rubbing something that feels slick, it's probably basic. We've seen a hydrogen atom. Here's a hydrogen ion. What's the difference in the hydrogen atom and a hydrogen ion? Yeah, missing the electron. A way to memorize the difference in an acid and a base. Bad. I don't make these up. I'm not a chemist. I'm a physicist. But that bad case, Bronsted Lowry, that's bases accept protons, acids donate protons. So base accept, acid donate is what that mnemonic is. It's a way to help you remember what's an acid and a base. So I'll write it on the next couple slides as we think about these. So bases accept, acids donate. Here we have a chemical reaction. This is, you put hydrogen chloride mixed with water, and you'll have a chemical reaction where the H and Cl separate, and you form H3O, hydronium. So the name for this thing here is hydronium. So the hydronium has an extra hydrogen on it. So now if we look at this, what did the HCl do? Did it donate a proton, or did it accept a proton? If it went from HCl to Cl, did it donate a hydrogen or did it accept a hydrogen? It donated. So that means that the HCl, since it donated, it was an acid. The H2O, the water, what did it do? It accepted, and so that was a base. So in this case, the HCl was an acid, we call it hydrochloric acid, and the water was a base. Water doesn't have to be a base. Water can be both a base or an acid, depending on your situation. Hydrochloric acid is a very strong acid. Like I said, it's one that you certainly would not want to mess around with. It will damage you. Here's another reaction. Water again and ammonia. The ammonia, did the ammonia donate a proton or did it accept one? It accepted. So that means that it was a base. This here is called ammonium. Okay, come on. You can see the hydronium was water with an extra hydrogen. Ammonium was ammonia with an extra hydrogen. So that must be indicative of getting that extra hydrogen on there. And what about the water? What did it do? Did it accept or donate? It donated, so that made it an acid. So in this example, water was an acid and ammonia was the base. In the other example, it was the hydrogen chloride that was the acid and water was the base. So there we saw two different reactions. One with water is the acid, one with water is the base. What's the difference in this slide and this slide? Let me zoom out a little so you can see them both. What's the difference? The direction of the arrow. In chemistry, we'll have reactions. I was supposed to talk about reactions in class already, but I didn't. So I'm going to have to, this lecture is one lecture ahead of where we should have been. So I'm going to lecture on the reactions tomorrow. But in the chemical reactions can actually go both directions. And so it depends on the concentrations which way it's going to go. So we usually combine these to show a reaction like this. It has the arrows both ways because it can behave as, it can go one direction or the other depending on concentrations. And so this here has it marked. On the left-hand side, we had water was an acid because it donates a hydrogen. On the right-hand side, OH is that hydroxide? OH is a base because if you go this direction in the reaction, the OH accepts a hydrogen. And the ammonium here is an acid, the ammonia is a base for the reactions going both directions. Now, you don't have to pull out your clickers. I don't have the clicker stuff set up, so I'm not taking track here. When water behaves as an acid, what does it lose? Blurt it out. There's two options that are hydrogen. It's actually the hydrogen ion because it's a proton, that's right. So it's losing the hydrogen ion. Salts are a general name. I said this in class yesterday. Salts are a general name. Salts are the precipitate you get when you mix an acid and a base. So here's some examples of salts. If I take hydrogen cyanide, we all want to not take hydrogen cyanide, just for the record, right? Because that's kind of a poison. And we mix it with sodium hydroxide, and you can see NaOH, HCN, cyanide is carbon, nitrogen. Then it's going to form NaCN. That precipitate is by definition a salt and water. Now, the things over here, the acid and the base, could be very damaging by themselves. But when you put the acid and the base together, they neutralize so that your salt is going to be far less damaging, far less corrosive than either the acid or the base. And you can see some other ones here. Hydrogen chloride and calcium hydroxide will give you calcium chloride and water, hydrogen fluorides. So there's a whole big group of salts. As the textbook says, there are as many salts as there are acids and bases. So table salt is not the only salt. And, well, not there. Here is a special one. This is Sudafed, or pseudoephedrine HCl, if you go to buy pseudoephedrine HCl. This here is the actual pseudoephedrine. And then if you bring an HCl, hydrochloric acid, there's no water involved here, unlike what we've been showing before. You will have this nitrogen with 2 bare electrons will actually snap up a hydrogen because those 2 bare electrons. So then you have a bond. The hydrogen is bonded. And then the chlorine is like, hey, look, I have a charge that attracts me, and the chlorine will also be attracted. And so this is the pseudoephedrine hydrochloride. When you buy Sudafed or you buy a generic version, it's pseudoephedrine HCl. It is the one on the right there, which is a salt. So that medication is a salt. But you're never going to say, oh, I'm going to just use some table salt instead of the pseudoephedrine because it's a salt. They're very different types of salts. What salt forms from the reaction of hydrogen chloride with potassium hydroxide? So that means that I'm going to have HCl plus KOH yields. Now in this, we've learned about HCl already. Is HCl going to be a base or an acid? It's actually the acid. It's okay, you have, right. That's going to be an acid, which means it does what to hydrogen? Does it accept another one, or does it give one away?
Yeah. No, I can't. Wait.
So that's base, That's acid. Is it going to be donating a proton or accepting a proton? Donates. So that means it's an acid. It's donating an electron or a proton. Wow. It's donating a proton. And so what I'm going to get from this reaction, if it donates a proton, I'm going to have the Cl by itself. And there's my reaction. Notice I had Cl minus and K plus as intermediaries when my acid and base separated. And then I have, what kind of bond is going to form between the Cl minus and the K plus? If I have a negative ion and a positive ion, they're going to have it will be neutral when they come together, but what kind of bond will they make? Covalent, polar covalent, or ionic? It's going to be ionic because they're two ions. When you have ions, when you have, one's a positive charge, one's a negative charge, they're going to form an ionic bond. So salts are ionic compounds. They're the precipitate when you put an acid and a base together. So our correct answer here was potassium chloride. If you have, quote, salt-free salt, or is that what they say, salt-free? The sodium-free salt, it's potassium chloride they usually use. Now you can also have iodized salt. Iodized salt, they're going to replace the chlorine. If you look on the periodic table, 2 below chlorine is iodine. And so it's going to be a salt that's made of, it's probably called iodic acid instead of hydrochloric acid with the precipitate. Now, the relative strengths of acids and bases is what the pH is all about. That's what our lab today is going to be exploring, the relative strengths of acids and bases. So how do we determine the relative strength? We determine the relative strength by looking at the concentration of either hydronium or hydroxide. And the one that we have by default, especially for class of this level, looked at is the hydronium. And so we measure something that has to do with the concentration of hydronium. The higher the hydronium concentration, the more acidic it is. So let's look at how this is done. Now notice that weak acids, things that aren't very strong acids, that means that they don't have much that will undergo a reaction. Most of it will be unreacted. You won't have a high concentration. And you can measure these. This is not what we're going to do. Let me pass over that. And we've already talked about water can be both. In water, if you look at the concentration of hydronium, you find that the concentration of hydronium is 10 to the minus 7th molar. We learned what molar was in class yesterday. Do you recall that? And if you don't, just say no. Okay, I saw some people nodding their head yes. What does molar mean? Moles per liter. When you do the molarity, it's the number of moles of solute per liter of solution. And so concentration of 10 to the minus 7 molar means it has 10 to the minus 7 moles of hydronium per liter. I thought maybe he had the molarity put on these. What was the liquid we used in lab last time? You want to go ahead and grab it, Alex? Because he marked on it what the molarity is. Make sure you have the one that has molarity in case there's more than one. Oh, wait. I returned them. Forget it. I returned them. My mistake. Well, one of the fluids we used in our last lab, it had the molarity marked. I think it was like something like 7 molar or something. This is a very low molarity, very low concentration. To determine if something's an acid or a base, we look at the concentration of hydronium compared to hydroxide. And if you have more hydronium, what is that going to do to the hydroxide? What do you think? Are they going to go up together, or is one going to go up and the other go down? Okay, one goes up, and what does the other do? Go down. Okay, that's what happens. When you have the reaction go, you either form more of one or more of the other. And so you can, well, where's my pretty pictures? Here's my pretty pictures. If it's acidic, you'll have a higher concentration of the hydronium. If it's basic, you'll have a higher concentration of hydroxide. Now, what we're going to do is do a calculation. And this is the definition of pH. pH, I don't remember what the P stands for, but H is for hydronium. It's a measurement about the concentration of hydronium, and it's a log base 10. If you don't have a base, that means it's a base 10 of the concentration of hydronium in molarity. Now, how familiar are you with the log scale? Little, a lot? Not very much, right? There's not a lot of math requirement for this class, so I expect most people there's not. So here's what log base 10 means. It's what power do I raise 10 to get x? Now, you look at that, and at first it seems like, well, that doesn't help me. That's just more gibberish to add to gibberish that the teacher's already throwing out there. But let me give you an example and then look at those words. Log base 10 of the molarity, the concentration, of hydronium in pure water. That was 10 to the minus 7th. So using this, what power do I raise 10 to get 10 to the minus 7th? Yeah, -7. When you have that definition, and then you look at it, it's 10 to the minus 7, it's very easy. Well, I raised 10 to the minus 7 to get 10 to the minus 7. Kind of redundant, right? So that's -7. So that means that the molarity, or the pH of pure water is minus log of 10 to the minus 7, which just means minus a minus 7 or plus 7. So that's the pH of pure water. Now, if it has a higher concentration of hydronium, what's a higher concentration? Like, let's just say this 10 to the 7th. Let's say that I had something that's 10 to the minus 3 and something that's 10 to the minus 10. Which of those is a bigger number? Okay, we had one of each. Like a million is bigger than 1. Closer to a positive infinity. I'm just asking about these numbers. Which number is bigger of these two numbers? Okay, so this one here is the bigger concentration. Now, if I put those into my pH calculation, if I have the pH is equal to minus log base 10 of 10 to the minus 3, that's equal to minus parenthesis minus 3 is equal to 3. So the higher concentration of hydronium is a smaller pH. And the lower concentration of hydronium is a higher pH. So going back to the concentrations. It didn't change color. There. So that's a bigger concentration of hydronium. If it has more hydronium, is it an acid or a base? I know we're still in the learning stage, so you're like, ah. It's an acid. Therefore, a lower pH is more acidic because the bigger concentration turned out to have the lower pH because of the minus sign in our calculation for pH. So the lower the pH, the more acidic. The higher the pH, the less acidic or the more basic. And 7 for the pH is what we consider neutral. So a pH of 7 is neutral. A pH lower than 7, is that acidic or basic? Acidic. Lower is acidic. So 7 is neutral, below 7 is acidic, above 7 is basic. Now here's a question that lots of people will get wrong if they haven't gone through more chemistry than you have at this moment in time. Right after I ask the question, then we'll answer it and then you would get it right. What is the minimum and maximum for pH? A lot of people would say 14 to 0, but that's not right. We're looking at concentrations and taking that exponent, and you could get a lower and lower and lower concentration or higher and higher concentration, and you can go to negative pHs or to pHs that are bigger than 14. They're unusual, but they occur. In fact, I'll show you a graphic with some common substances and their pHs, and it'll have one that's a -1 pH. -1 pH, is that acidic or basic? It's acidic because that's low, right? That's lower than 0. So that's a highly acidic thing. You wouldn't want to touch it. Okay. NaOH. If you put NaOH in water, it's going to separate. And what's going to go up? The concentration of hydroxide or the concentration of hydronium if Na and OH separate? If I have water by itself, it's going to have an OH concentration of 10 to the -7. And I put NaOH in so that Na and OH separate. What's going to happen to the concentration of OH? It's going to increase. So if the OH concentration increases, then is that a base or an acid? That's right. Because OH increase means H3O decreased, therefore base. Oh yeah, this was showing just another number. I was like, I don't know why I have this again. Oh, it has 10 to the -5. Well, we've already done more than one example with that. And 10 to the -9 we've already done. Here's the table coming from the textbook of pHs. And you see concentrated HCl -1. Doesn't have to be between 0 and 14. The highest that it's showing here for pH is oven cleaner. Neutral is 10 to the -7. Let me just mark that. Pure water is 10 to the -7. Notice blood is not neutral. Your blood is it acidic or basic? It's slightly basic, which means that your blood is going to have a slightly, what kind of taste? It's really slight. I don't think you would taste it. Furthermore, I'm not going to try tasting my blood or any other animal's blood.
Sweet.
No.
Iron.
Bitter. Bases are bitter, acids are sour. So it would have a slightly bitter taste. So I don't know. I don't eat meat, so I don't know what meat tastes like. But
It's not really bitter. It's just. So
acids are the sour ones. And the stronger the acid, the more sour it's going to be. Things like hair remover. What's the hair remover doing? It's dissolving hair. You probably don't want to spend too much time with that. Your blood being slightly basic, it's not a problem. You don't have to worry about, get the blood on stuff. And even like right after Amy and I got married, we came back through Yosemite. We stopped at Mono Lake. Mono Lake is actually a very basic lake. You feel the water. What does the water feel like? If it's basic, it's going to be slippery. So you touch stuff in the water and everything feels very slippery. And it's not basic enough to cause any problems. It's not going to dissolve your hair. There are animals that surprisingly can live in it. One thing that you might have heard is people who monitor their body pH. Your body pH is actually very tightly set by your body. You can only live with small variations in your body pH. So people who are trying to monitor their body pH are, for the most part, wasting their time because they're either dead or their body pH is going to be where it's supposed to be. That said, one of the things they do is measure the pH of their urine. Well, the pH of the urine will tell you how your body, what it's getting rid of to maintain the pH level. So that could have some indicative information for health. But just your blood pH, it's going to be right on. There's no point in poking yourself and measuring the pH of the blood. And so for today's lab, we're also not going to poke ourselves and measure the pH of our blood. We do poke ourselves occasionally for labs, but usually it's for biology labs where we test your blood type. Just a few things on acids and bases before we get started with the actual experiment. So acid rain. You guys have you heard of acid rain? Acid rain is a real problem. It's called acid rain if you have a pH lower than 5. Remember, what is neutral pH? 7. So pH lower than 5 is a pretty good acid. That's a high enough pH that it will do things like dissolve marble. Marble is actually water soluble, but it's very slow in being dissolved by water. But if you have acid, it's much faster. In fact, one of the ways that geologists will test to see if something is calcite, marble is a metamorphized calcite. That means it's a calcite that has been put under pressure at high temperature and it's flowed a little bit. So one of the ways they test to say, is this calcite or is this like some other mineral, is they'll have a little bottle of acid. They just put a little acid on there. If it bubbles, it's calcite. That was one of the tests we did in our last lab. Questions?
What's calcite?
Calcium carbonate.
Oh.
Sorry, I should have said that. So how does acid rain form? Acid rain forms when you have burning coal or oil, such as in the Rust Belt states where they have a lot of iron and steel works. They burn a lot of coal. You release a lot of sulfur into the atmosphere, and that sulfur then is going to, in the air, produce sulfuric acid when water comes through, and you get the acid rain. Now, ocean basins tend to be basic. And, well, here's showing some effects of acid rain. You have I don't even know what to call that thing. It's an obelisk with hieroglyphs, right? Yeah, I think that must be hieroglyphs. You can see a lot of deterioration because acid rain has deteriorated that obelisk. When you have acid rain, it's going to cause you to have calcium carbonate, rock dissolve. One of the things that's important for our planet is that carbon dioxide is absorbed by water and then deposited as a rock, the calcium carbonate, the calcite, or limestone is another name for it. If you get an acid rain, the acid is going to dissolve that calcite and change the entire ecosystem. And that's where I'm going to stop the lecture, mostly because that's the end. So I've only lectured for less than 40 minutes. Let's get to the lab. We don't need to take a break. So for the lab today, not homework, lab. For the lab, we are going to be measuring pH. So Alex and I have ever so carefully prepared. We have all of these things here. Red cabbage, check. Cooking pot. Haven't used the cooking pot because I did this all in my little beaker. You do need to wear glasses. Put them on. Even though right now what I'm doing is purely safe, I'm just working with our little, now. I think I returned the cool ones Alex and I wore. So here's my broth, cabbage broth. You know what I don't like? Cabbage. So dump it out, and everything is draining into there, and then I'm just going to pour the water back into here, and this is what we're going to use to measure pH. My wife approved of me taking these things from home today. Last year I didn't ask her. That was not the wisest decision. Okay, a lot boiled off. I fear that Alex and I will have to right away start making some more. This is what we're going to use to measure pH. So you're going to take this, get a nice little glass beaker here, pour a little in. I'm going to try to preserve something. I don't have as much as I thought. Wow, that is really dark.
You can just add some more to it.
Yeah, I think we probably want to.
But you might want to make sure it's... Did you use normal water for that?
Yes, I did.
Okay.
I'm going to dilute this a little. That still looks pretty dark.
Yeah, that looks really strong.
Okay, so let's dilute some more. Well, we might have plenty if I have to dilute this a lot. We'll see how it works. Okay. I take a tiny amount, filled it most of the way up. Now let's put something in. What would you like to check first? Club soda. Okay, so I'm just going to put a little bit of club soda in and see how the color changes. What color is that now? What color is that now?
Purple, dark purple.
Okay, it's kind of a bluish color. Now I'm going to put just a little bit of club soda in. I'm not going to fill it or anything. So I put a little club soda in, and what's happening? Okay, it's turning more purple now. And so what I need to do then is look at my table and say, what color is that, and what would that represent for pH? So you have here color coding. And so what I want you to do is notice we have more samples than there are lines for. They actually give you less lines than they recommend samples, and I added one. So this was club soda, and so I'm going to put the color. So my color is a light purple. And then I'm going to try to estimate the pH. So light purple is going to be somewhere in this range. And I'll be like, I don't have any experience now. So maybe I should guess that it's right in the middle of light purple because, you said light purple. And if it's very clearly light purple, it's probably somewhere near the middle. If it was close to a pinkish red, then I would go closer to the 6.5. So I'd make, if it was a pinkish purple, I might say 6.7. But this is somewhere in the middle, so I'm going to go somewhere about 6.9. And so that's my estimate based on using this. Now, you would not do the next thing I'm going to do. You would now dump it out, rinse it out, put some more in, and go on. But I am going to see what happens when I put I'm putting borax in because that's the one that's open. Put a little borax in. So I put the borax in, and
I think you have too much liquid for how much you're putting in.
yeah, I might. I clearly have more than the recommended, was it 50 milliliters? Did it say 100?
Yep.
Yeah, I didn't see much change here. Probably part of the reason why you don't mix the two. Make sure that after you use one of these, you clean it off. And so you're going to go through and you're going to test each one of these substances, report the color you see, and estimate the pH. So I do believe that I will dilute this incredibly, and we're ready to get going. Do you have questions? Yeah.
So you want us to do all of them even though there's not the space for it?
Right, you'll just have to do like I did here and split 3 of them. Well, split 3 of the things in the table so you can put 2 on them.
So I have a question also.
Go ahead.
Every time we test something, we have to dump it out?
Yeah, after you're done, after you identify the color and everything, you dump it out and go on to doing another one.
All right.
You almost slightly see through it. I think it usually was.
I really got a lot out of this by letting it sit for a long time. It's still pretty dark.
If it's too concentrated, it'll take a lot of experience.
Well. This here should change color just by going red, so.
Oh, that's nice. Look.
It's over.
I think it's good because we put it in.
I really made a lot. Or got a lot out. Okay, that's at least.
Unfortunately, we don't have enough goggles if I wear them. So.
We should. We should. We had enough last time. Where are the other two? The cool ones that you and I wore.
Painful ones that dig into your ears.
Here's the cool ones.
Ah, there we go.
Yeah. Don't need that. All right.
Do you have the batteries too?
What we're going to use for that is not actually a battery, but something that works